just because I think that it will not be worth my time or your time. So we are still going to meet here, obviously from now on in Google Meetings instead of or instead of Zoom. And I think we're still going to meet every other day. So Monday, Wednesday, and Friday at 1 o'clock. I'll be posting those links and instructions for how to use Google Meeting on the classroom. And we're just going to go over together the free response questions. Now, to give you guys some accountability and to give you some points, participation points in this class, I am going to be posting assignments in the Google Classroom for you all to just show me an uploaded picture or something that you've worked on the free response questions, okay? And I'm gonna do that every Tuesday and Thursday evening. So basically, every Tuesday, Thursday night, you guys will have an assignment due on the classroom just to show me the work that you've done on the free response questions. And then Monday, Wednesday, Friday, we will go over the free response questions together. Does that sound fair and an okay plan? Okay.
Yeah. Will the assignments be like specified problems? Like
yes.
You need through here. Okay.
Yes, they will be. Yep. All right. Any procedural housekeeping questions before we start looking at stuff? Okay, so you need to have access right now to probably your notes if you think that would be helpful, maybe an AP equation sheet, which everyone should have, and you need to have access to that document of the free response questions that I have given you previously.
1 second. I'm going to go get access to a turkey sandwich.
Oh, Lord. Miss Rahman, why ain't you sleeping, girl?
First of all, homework, and second of all, my uncle was paying me to take the data from a retirement home and put it in a spreadsheet. So I spent all night doing that.
Okay.
Now I have to burn my computer. So.
You have all these old people's social security numbers that you can steal their identities.
Yeah.
All of my what was I gonna say?
Yeah, I'm back on my sandwich.
How is it? Is it good?
Can we see this?
What kind of toppings we got?
Yeah. Wait for it.
It's better be worth the wait.
Yeah, I came back to Zoom just to see. Oh my goodness. Also, I feel the violation of privacy is really on Zoom's part. When I was just chilling on another tab working on something and Mr. Thurman decided to screen share and it thought it was going to commandeer my screen and yoink me back to Zoom to show me what he was looking at, which was helpful, but still.
Did you just change your shirt?
Yes, because I felt called out by Grace.
This is the proudest moment of my life.
Must have a really sad life then.
All right, guys, let's get started.
Oh my God!
Boom!
All right, you guys should be seeing
Learn from your mistakes.
You guys should be seeing the Word document on my screen. Yeah.
Mm-hmm.
Yes. Okay. All right, so I'm just gonna get started working through these one at a time. I think I asked you guys to try to do 1 or 2 a day, so hopefully you've gotten through the first 3 or 4. Of course you have. So hold on, let me pull up the chat. All right. Okay, so let's look at this first question. Can you guys see my writing on here?
Yeah.
Yes. Okay.
Excellent. No.
Well, you weren't looking at the screen at the appropriate time. All right, so we have this conducting solid sphere. We haven't done questions like this in a long time, so this is going to be a really good review, I hope. We have this conducting solid sphere, radius A, and it is charged to a potential of V. First of all, can someone tell me what is meant by this term potential? What is the electrical potential? Someone remind us what that concept is.
Potential at the surface.
Say that again, Mr. Williamson.
Potential at the surface.
Well, okay, so it's true that this is a conducting sphere. So it's true that it's holding all the charge at at its surface, and that this value V is some value at the surface, but also all the way throughout it. So hopefully you guys remember that conductors, every part of a conductor is
Equipotential.
exactly equipotential. So the whole thing has a value, a potential of V, and that's equal to, as Mr. Williamson said, what the V is at the surface. But the question I asked is, what even is potential? Like, what even does that mean?
Like voltage or potential difference, or is that the same thing?
Same thing. What is it? What does it mean?
Uh,
Anybody?
Ouch.
that's a good question.
It is. All right, so let's go over it. Remember that we define an electric field as what? What's the basic definition of a field?
The
F
negative.
over Q.
Yeah, okay, so F over Q. That is like the definition of an electric field. It is the electric attractive or repulsive force divided out by a test charge. So remember that the electrostatic force, F here, is governed by Coulomb's law. This is a big throwback. There's my K value, and then Q1, Q2 over R squared, just like that. Coulomb's law allows me to find the force of attraction or repulsion between two charged particles. So if I had a charged particle here, Q1, a charged particle here, Q2, or something like that, I could find the force of attraction or repulsion. If I have a collection of charged particles and I wanted to know the attractive force or repulsive force on this particle Q3, I would have to do like vector addition. So hopefully you guys remember that. And we said that it is much more convenient for us, instead of thinking about how a particle here at this location would feel forces from this particle and this particle, it's more convenient for us to instead just describe how space itself changes. So if we had a point P in space here, we could say, what are the potential forces that may show up due to this arrangement of these charged particles? How do these charged particles change space around them such that they give rise to forces that could show up if a charged particle was located at point P in space? And we refer to that as an electric field, where the electric field vector is just the force vector divided out by a charge. So instead of describing a force, where a force is an interaction between two things, we're describing what space is like due to an arrangement of charge. In the exact same way, voltage or electrical potential is defined as potential energy due to an arrangement of charges divided out by a test charge. So just like field describes what space is like due to an arrangement of charges, voltage or electrical potential describes what space is like due to an arrangement of charges, not from a forces perspective, but from a potential energy perspective. All right, so it's like potential energy, I think. What was that, Mr. Moore? Do you have a question?
No, sorry. I was just seeing how I could arrange the screens and stuff, and it said request access to control Chad Thurman's screen. And I said yes.
Yeah, I declined that. Does someone have an actual question about this?
No, sorry. I was trying to set up my deal over here so I can see better.
Okay, any questions about the concept of potential? All right, several things we need to remember about potential. All parts of a conductor are what we call equipotential. So Mr. Williamson, Mr. Rahman said this earlier. The voltage has some value at the surface of this sphere, and it's going to be the same value all throughout the sphere, okay? So the voltage does not change as we move through the sphere. It's the value at the surface. Does anyone remember, this is something good, I did recommend that you guys memorize this, the voltage for a spherical conductor. We have an expression for it. Does anyone remember what it is?
KQ over R.
Excellent. KQ over R, where R is the radius of the sphere. So if I were you, I would memorize that. Do you have to memorize it? No. You can derive it. Let me show you how you could derive it. You can derive it based on this equation, that potential difference is the negative integral of field dot dr, where this is the field vector and this is the position vector. So if I use this approach, I can calculate the potential of the sphere. Now this equation is potential difference, so it really gives me the difference in potential between two regions. But all you have to do is remember that we define the potential at an infinite distance away from the object. We define that as a potential of 0. So what I can do is I can perform this integral from infinity to a radius of a. It's like I'm coming out from infinity in to a radius of a. And then all I have to do is just plug in an expression for what the field is. Now, this would be something else you would have to memorize, or we could use Gauss's law really quick, I suppose. But does anyone remember what the field is at the surface, at and beyond the surface of a sphere?
0?
Nope. Inside it's 0. As long as it's a conductor. So yeah, these are things that we have to remember. The inside of conductors have a field of 0, but at the surface and beyond the surface, it's kq over r squared. Yeah, exactly. All right. So I plug that in here for field. You perform the integral from negative infinity to a, and you will get kq over a, where a is the radius of this sphere. So that's one way you could have derived this. So you could have memorized this, or you could have used this, and you would have had to memorize what the field is like at the surface and beyond of a sphere. I would memorize these things if I were you guys, all right? So part A then becomes really easy points. If I want to know what the charge on the sphere is, well, we've just said either through memorization or through derivation of that integral, we can show that V is kq over r, where r is the radius of the sphere, which here is a. And now all I have to do is rearrange this and solve for q. So q in part A of this question equals v over k times a. Someone remind me, what is this k that we're throwing around?
1 over 4
Yeah.
something.
Yep, it's
Or
that.
epsilon naught.
Yeah, 1 over 4
Yeah.
epsilon naught. It's that Coulombic constant.
What was that? What's that called again? The permittivity.
The epsilon naught is
That's epsilon naught.
Epsilon naught is the permittivity of free space. Yeah. Okay, so this will be the answer right here to part A. Are there any questions at all about that? You guys feel okay? All right. Excellent. Ooh, Mr. Moore gave me a real thumbs up. All right. Okay, so then we very carefully wrap this conducting shell around the sphere. It does not matter at all that we're building this out of hemispherical shells. That's just they're saying like, hey, you're able to wrap this shell around by constructing it in that way. And then this outer one is connected to the ground. So if we imagine, therefore, that this sphere right here has a positive charge, positive q, which we just described what that was in part A, what is going to happen to this outer sphere?
Negative q.
Yeah, excellent. It's going to develop a charge of negative q, won't it? Yeah, so whenever we first wrap it around here, so let's imagine that we don't connect it to ground yet. So let's forget that. Whenever we wrap this around the interconducting sphere has a charge of positive q. If the outer shell is not connected to ground, what is it going to do in terms of its charges?
They're going to move to the middle.
Yeah, I'm going to have separation. I'm going to have separation of charge, won't I? So The electrons of the outer shell will be kind of sucked in to the inner surface. So that would get me a charge of negative Q right here on the outer surface. And then that would leave a positive Q then on the outer surface, just like that. What is going to change if I connect it to ground? Who knows?
I'm going to supply electrons to...
Yeah, so remember that the ground is always going to be a source or a sink of electrons,
Electron sink, yeah.
depending on the circumstance. And in this case, is the ground acting as a source or a sink?
Source.
A source, excellent job. So it's going to be a source because the part that's connected to ground now has this positive charge. So right now, before I connect it to ground, I would not say that the outer shell is charged. It just has a separation of charge. It's been polarized. But once I connect it to ground, the ground is going to provide a source of electrons. Electrons are going to flow up. And now this whole thing is going to develop a charge of negative Q overall. In other words, I'm going to get enough electrons to cancel out this positive Q that it had there on the outside. Do we feel okay about that idea? Any questions at all? Okay. That's called charge by induction. Hopefully you guys remember that. This positive object that I hold near this one, and then I connect that outer one to ground, is going to give this outer one the opposite charge that the inner one has. Okay, so what I'm trying to do now is derive an expression by using Gauss's law, and we have not used Gauss's law in a really long time. Sorry, let me zoom in on this a little bit. Derive an expression using Gauss's law for the electric field that is in here, in between A and B, in this empty space. So someone remind me what Gauss's law is all about. When do I use it? What is it for? What does it help me find?
Uniform field that you can, or field that you can enclose and approximate using like a known volume to approximate the field coming out of an area.
Okay. Yeah, basically.
For irregular shapes?
For what?
Irregular shapes?
Irregular?
Well, like not like a sphere or like something.
No, Gauss's law does, like the whole point of using Gauss's law is to take advantage of symmetry.
Right.
So I do want to use this for like spherically symmetrical objects, or yeah, so maybe we should remind ourselves when we can use Gauss's law and what is it for. We like to use Gauss's law. Well, first of all, someone just tell me the equation for Gauss's law.
Q enclosed equals the surface, or the integral of E dot dA.
Excellent.
Wait, isn't it like Q enclosed over epsilon naught or something?
It is.
That too.
Yeah. Okay, so this is Gauss's law. And this little integral here is a surface integral because it's telling you to integrate it over a Gaussian surface, where the Gaussian surface, as you guys hopefully remember, is an imaginary surface that you draw to help you determine what the field is like. Okay, this gives you something called flux. So remember that flux was this little letter. And flux is like how much field is passing through a certain area, and it's a dot product. This is getting a little bit, you know, we might analyze exactly what a dot product is and what flux is later. But the whole point of Gauss's law is that it makes this integral really simple. In fact, you should never have to integrate with Gauss's law, because this field is going to end up being constant across the Gaussian surface that you draw. Mr. Moore, you have a question?
Is this the concept in class where we drew that box that we thought about water going through it and where we turn at different angles, there's less or more? Is that flux in this?
That is flux, yes, correct. Yep. Very good. Okay, so the whole point of Gauss's law is to draw or manipulate an imaginary Gaussian surface that has field passing through it, and to draw it in such a way that this integral becomes really, really easy for you. So in other words, I know that there is field. Remember, we can draw field lines. Field lines always go from positive to negative, don't they? So I know that there's field in this region. And I can draw then a Gaussian surface, which would be a sphere that would, so that's what I'm drawing in pink here. And that Gaussian surface has a radius of r. And if I look at this carefully, I can see that everywhere around my Gaussian surface, where the field passes through the Gaussian surface, the field is uniform everywhere there. There's no difference in field here, 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 here. All around this sphere, my Gaussian sphere, the field is uniform, it's the same. So I can pull it out of the integral. So the whole thing then just becomes E times the integral of dA, where dA is a derivative of area, an infinitesimally little tiny piece of area, surface area of the Gaussian surface. That equals Q enclosed over epsilon naught. Sorry, Mr. Narayan keeps getting kicked out for some reason. So if I integrate all the little tiny bits of surface area all around my sphere, I just get the area, the surface area of a sphere, which is 4 pi r squared. So I get E times 4 pi r squared equals Q enclosed over epsilon naught. And remember that we already had a statement for Q, didn't we? That was what we found in part A. And in part A, I think that we found that Q was B over K times A. So I can plug that in right here, rearrange, and solve for field in this region. Now notice that we have two different radii going on here. I have the radius of A, which is the radius of the actual sphere, which is trapped up in my expression for what the charge of the sphere was. And then I have radius of r, little r, which is the radius of my Gaussian surface. That little r is a variable. Like I could have made my Gaussian surface have any radius from A to B, and I want it to be a variable because I'm trying to describe what the field is like in here. And of course, it's going to change as I move away from this sphere and move towards the shell. So we have this expression, we have an expression for charge, we combine them and rearrange, and we get that the field is equal to VA over R squared. You may be wondering where the 4 pi and the epsilon naught went to. Well, because my Q has a K in it, and K is 1 over 4 pi epsilon naught, it ends up getting canceled out. So this is the field. How do we feel about that? Feel okay?
If we wrote it without like canceling everything out, would we get it wrong?
Oh my. I think that Satan himself just answered your question for you. You know, Mr. Wisdom, you always want to try to be as algebraically simple as you can. I'm really not sure, to be honest. All the solution guides have this answer in them, so I'm not sure what kind of points they would give you for not canceling crap out. All right, any questions about A or B right now? You guys feeling okay? All right. So let's keep going on to part C. I'm wondering if we should actually take a moment to remind ourselves what flux even is and how it works. Probably it would be worth our time. Although I can't see them asking you many things about flux in general on the free response portion. Okay, well, let me just remind you what flux is. So here's a general statement about flux. If we have an electric field that is like this, and let's say that we have like so there's my field E, and let's say that we have a like a rectangular little hoop that we're putting in the field, and the field is not really passing through. Fields don't move, but we can imagine as if it's flowing water or something. Then flux is all about like how much flow is there across that surface. And what I can do is for this surface, I can draw what is known as an area vector, which is just a vector that points perpendicular to the surface area. So my area vector will be pointing like this. You guys remember this?
Is that the thing with like the carrot on top?
We can we can express it just as so the thing with carrots, yeah, I think we called it the normal vector with like that.
There we go. Yeah,
So that's just saying, so that's just a direction. And that's just saying
Okay.
that, hey, the area vector has the size of the area, and then it has a direction that points normal to the surface area. So that's just the term that defines the direction for you. Yeah, good remembering that. So of course I'm going to get maximum flux through here when the area vector and the field vector are parallel to each other, right? And in other words, if I draw those two vectors, my area vector and my field vector, if I draw them tail to tail, then the angle theta between them is 0. And what trig function has its maximum at an angle of 0? It's a cosine. And that's why we take the dot product. We say that flux here would be the dot product of E dot A, because a dot product worries about the cosine of the angle between the two vectors. So that's flux. If I were to like tilt that little rectangular hoop up, then my A vector would be pointing up like this. And now there would be some significant angle between the two vectors if I were to draw them tail to tail. And the flux would be, once again, EA cosine theta, where I'm worried about how much do they agree with each other. So A cosine theta would be this component of A right here, which is how much of the area vector lies along E or something like that. So anyway, that's flux. And whenever we have a changing irregular shape, or a curved shape rather, so if my area is changing or the field is changing, then I have to do an integral, which is where Gauss's law comes from. It's a surface integral because the surface that I look at is enclosed. Your Gaussian surfaces will always be spheres that you wrap around. What else counts as a Gaussian surface? Y'all remember?
Who knows?
A cube.
Cube could be a Gaussian surface. Yep. What else?
A cylinder.
Excellent. A cylinder.
We love our cylinders.
Yes.
Wine bottle.
What are you saying, Mr. Williamson?
Wine bottle.
What did we say about that? I think that we said that no, it's not, because I don't remember. Anyway, okay, blah, blah, blah. We'll see more Gauss's crap come up later. Okay, part C. Part C, I think, was the hardest question on this. So determine the potential of the solid sphere relative to the ground, or relative to ground, rather. So what the heck is that asking? Like, don't we already know the potential of the solid sphere? Well, we know the potential of the solid sphere was like V, but that's like measured from infinity. We want to measure it from ground. Well, what do I know is true about the ground down here? It is connected to sphere B. And therefore, because sphere B is a conductor and this is a conducting wire, I know that technically speaking here, conducting sphere B and the ground must be equipotentials. So really what this is asking me to do is find the potential of sphere A kind of from the perspective of sphere V. So that is this. I'm trying to find the potential difference between the two, basically. Hold on, my pin thing is not working for some reason. There we go. I'm going to perform this integral from A to B, basically. Does that make sense to everybody? This was the hardest thing to set up. Hey guys, I don't know what y'all are laughing at. You're being kind of disrespectful to me right now. Sorry, hold on. So please look at this and make sure you understand why this. What?
I'm being disrespectful. Jackson sent me a private comment, and I accidentally said you're welcome to the whole class. That was it. I'm stupid. Fine.
That's fair. Okay. Look at this and make sure you understand why doing this will answer the question. We're trying to figure out like the potential difference between the solid sphere and the ground. What is the potential of the solid sphere relative to the ground? Well, the ground is equipotential with sphere B. So I can just perform this calculation. I already know what the field is like in between them. I answered that in part B. So my answer then is going to become the negative integral from A to B of
dA over R squared.
yes, thank you.
dr.
Dr, correct. What I'm realizing now is that I think we need to evaluate this from B to A because we're trying to measure it relative to ground. So we need to like start at the ground and end at sphere A is what we need to do. Not entirely sure it'll matter. Okay. Yeah, I'm sorry about that. Look at this and make sure this makes sense to you guys. If you can set it up, then you should be able to do the calculus to get it. We want to know the voltage of, so it's like we're moving now from sphere B to A. Earlier in part A of the question, I said that we could do this integral from like infinity into A to figure out the potential of A from a perspective of infinity. But now what we want to do is move from B to A because B is equipotential with the ground and we're trying to measure it relative to the ground. All right.
Why is B equipotential to the ground?
Because it's a conductor and it's connected through a conducting wire. Remember, all conducting surfaces that are connected are equipotentials, aren't they?
Oh, it applies to, okay.
Yep. Good question. All right. I'm going to let you guys do this calculus. But you know that it's probably helpful for you to rewrite R. So R is your variable of integration. You can rewrite that as R to the -2. and then the integral of that is negative r to the negative first, and then you plug in your bounds and you go from there. So that should be fairly straightforward integration. Anyway, when you do that, you end up getting v times b minus a over b. That is me kind of putting it in the most algebraically simple form that I can. Do you guys want to go over the calculus and the algebra, or are you good?
I'm good.
Make sure my answer is same value.
I'll give you a second to look at it.
Yeah, cool.
We good? Cool. Okay, excellent. So listen, if you're asked to find the potential of something like this, we've done this several times before, where we have to find the potential difference really between two surfaces. I remember some examples where we had like coaxial cylinders like this, like two cylinders wrapped around each other, and we had to find what the potential difference was here. That's what this question is asking. You're always going to do this integral whenever it's asking you to do that. All right. So we have that, and part D is asking me now to determine the capacitance of the system. Oh boy, we haven't talked about this in quite a while. Who can remind me what capacitance is? What does it mean?
Is it like how much charge it can store? Or something?
Kinda, yep. Anyone else have anything to add to that?
What charge per voltage?
Yeah, okay, so remember that capacitors are like, we talk about them like they're the springs of the electrical world. They can store energy based on something called capacitance. Just like a spring can store energy based on its spring constant, its stiffness. The stiffer the spring is, the more difficult it is to compress, and the more energy you store in it when you compress it. Same thing for a capacitor. Who can tell me what you have to have a capacitor? What must there be?
2 plates.
Potential difference?
Okay, so Mr. Moore got part of it, Ms. Rahman got part of it. Mr. Moore, you said 2 plates. Really, it can be 2 conductors that are near each other in any arrangement. Like, technically speaking, I have a spherical capacitor in this example. I have a sphere that's a conductor, and it is wrapped around with another sphere. So that would be a capacitor. If we had coaxial cylinders, one conducting cylinder wrapped around another with space in between, that would be a capacitor. Or
Are the
yes,
cylinder ones the most common in like electronics and stuff? Because I see, like, if I'm ever like playing with electronics, I have like
right.
Are they all the cylinder type?
Yeah, that's pretty common. Those are the ones that I have in my lab. Or Mr. Moore, there's another form of capacitor that we haven't seen really, where it's basically a plate capacitor that's been like coiled up really tightly. Does that make sense? It's been like wrapped up. Sorry, I thought I heard someone else jump in with a question.
Yeah, it was kind of a stupid question. I don't know why you would. Well, so on like capacitors with, I don't know why you'd know the answer to this, but the capacitors that we use like in class, why are they like rounded on both ends?
Rounded on both ends.
Like it's like kind of like, it's not like a perfect cylinder across, but
Oh, I
sometimes
see.
it'll be like.
Yeah, unfortunately, Mr. Williamson, I'm going to tell you that's a question for an electrical engineer. Like, maybe talk to Dave about that one. I'm not entirely certain. Okay, so someone tell me what the equation for capacitance is.
Q over V.
Yeah, Q over
Q
delta.
over delta V.
This is on your AP equation sheet, rearranged as this. but you can just very quickly unrearrange it to get this. So this is really simple. We have an expression for Q, and remember, capacitors are always two conductors, right? Like two conducting plates. In this case, we have a conducting cylinder and then a conducting cylindrical shell, don't we? So if the capacitance equation is Q over delta V, which Q are we talking about? Are we talking about the charge on this one or the charge on this one?
Either.
On either one, on just one of them, because they're going to be the same. Yep. So we just take the absolute value of one of them, right? Well, we have an expression for what that Q was, don't we? We got that in part A. And the potential difference between the two, we got that in part C. So really this is a simple question asking us to divide those. So the Q that we got earlier was V over K times A. And of course, we could change K into 4 pi, a 1 over 4 pi epsilon naught. And then the potential difference that we just solved for was V B minus A over B. So all you need to do is just use some algebra to simplify this down. So it looks like if I try to simplify this down, I basically have two fractions that I'm dividing by each other. Looks like I have a V on top here and a V on top here, so those are going to cancel each other out. I'm dividing this with a B on the bottom, so the B comes up here, and then I get a K on the bottom. So I think it's going to end up being AB over K times B minus A is the capacitance. And we should pause and see if this makes sense. Capacitance for any capacitor, hopefully you remember, it only depends on like the geometry of the capacitor. We had this thing that I encourage you guys to go back and look in your notes. We'll probably end up doing it by going over all these free response questions, where we derived an expression for the capacitance for different arrangements. For two spheres, just like in this question, we derived an expression for the capacitance of coaxial cylinders, for two plates. And the equations that we got always showed us that the capacitance of a capacitor just ended up depending on the geometry. So this equation is telling me that my capacitance will get bigger if A or B get bigger. And what do A and B represent in this situation?
The radii.
The radii of the two spheres. So why does it make sense that my capacitance gets larger if my spheres get larger?
They can hold more charge.
They can hold more charge, exactly. Very good. They can hold more charge per potential. And then down here, I'm seeing that I have this B minus A term. The capacitance will get bigger as that it gets smaller. And what is the meaning of B minus A in this instance? It's the distance between the two, right? So you guys should know that the capacitance gets bigger as the two plates of your two conductors get closer to each other, and that's exactly what this equation does. So I always encourage you guys to pause and see if your equations make sense. How do we feel? Good. Okay. So did you guys actually do this problem before we went over it, or no? Maybe a couple of you did. Okay. So remember that from now on, I'm going to be posting as an assignment in the Google Classroom, you guys turning in your work. So starting tomorrow, you're gonna have to turn in the ones that we're gonna talk about on Friday. Anyway, be on the lookout for that in the classroom. Okay, let's go on to the second question.
You said you're gonna assign those, right? Like tell us which ones we need to do by Friday?
Correct.
Okay.
Oh, I guess I can make this big, can I?
That's what?
No. I should have known better, shouldn't I? I really need to not record these and put them on the YouTubes because I'm gonna get fired. All right.
What? That's what I was just thinking, you know? I was trying to say.
Right. Okay, this is one that we've done more recently, this circuit stuff. So first of all, someone tell me, why does it matter that the battery has been connected for a long time?
So the
Because it
capacitor.
means our resistors, our capacitors have charged.
Excellent. Yeah, I have a capacitor in my circuit, so that means that the capacitor has been able to charge, right? In other words, I've stretched the spring as much as I can stretch it, is another way of thinking about it. So if I have charged this capacitor to its maximum charge, someone tell me what is true about the circuit over here?
It's only going over the resistor. It's
Yeah.
avoiding the capacitor.
Excellent. There's no current flowing through this branch. So right now, I'm not worried about this branch of the path. Are you guys with me?
Mhm.
So I'm thinking about that right away. So my current then, if I wanted to like trace it out, it's going to go around this way. And then my 9 ohm resistor here is going to get like all the current, right? It's going to get all the charge flow. And then my current is going to branch into 2 paths, right here and right here, going around this loop. And then those are going to combine back to form the overall current going back to the battery. So I could write like I could write some loop rules and junction rules for this, but I don't have to. Remember, you only want to take the time to write loop rules and junction rules, those Kirchhoff rules, if you are unable to do what first? What should we try to do first always when we're analyzing a circuit like this?
Find current.
Well, that's true, and that's what the questions.
I guess.
Sorry, say that again.
Combine like resistance, find equivalent resistance.
Exactly correct. I need to see if I can combine easily the resistors into their equivalent resistances. And I can do that because what I have basically is a circuit that ultimately breaks down into 2 parallel pathways, right? Maybe I could call this path A and call this path B. Those are parallel to each other. So this is usually what you want to do first, is try to figure out the current in the overall circuit. In other words, what current is leaving the battery, what current is entering the battery. And that's what this question is asking, by the way. Question A, the current in the 9 ohm resistor is going to be the current overall, the total current in the circuit that's leaving the battery before it gets divided up at my junction here into path A and path B. So I need to start trying to collapse this down into its equivalent resistances. So which one would you guys start with first in order to do this? Someone said something.
Yeah.
Path B, the right path, right? So what is for path B? What is the equivalent resistance in path B? 12. Excellent.
Just add them, right?
You add them up. Yep. And I want to point out this is on your AP equation sheet. It says this RS equals the sum of R. Someone explain what that means.
In a path, you add up all the resistances in that path to equal their total resistance.
When they're in series, exactly. So I have basically in this path B, I have an 8 ohm and a 4 ohm resistor in series with each other. I'm not worried at all about this branch once again. So in path B, the equivalent resistance is 12. So in path A, the resistance is just 4. So I can now collapse A and B down and imagine that they were one path, and those are parallel. So what is the equivalent resistance like for path A and B together?
It's the sum of 1 over the resistances.
Is equal to 1 over the equivalent resistance.
Yeah.
So yep. So here's the equation that is given on your AP equation sheet, just like this.
What does the I mean?
The I means like just the number in the series. Like this is a series that you're summing together. So resistor.
Okay, so it's like just a placeholder.
Yeah, and it's telling you to start with the first one, basically. So you guys see what I'm doing? First, I collapsed B down and saw that it had an equivalent resistance of 12. And now I have A and B in parallel, and I can collapse them down into one thing. So 1 over their equivalent resistance across A and B is going to equal 1 over 4 plus 1 over 12. do the math. Don't forget to flip it over at the end, and you end up getting 3. Okay? Good job, Mr. Moore. We're all so proud of you. So, oh boy.
You not have a bigger eraser?
I don't. I can't change it. I can't change the size. Okay. So here's what I've done. I've collapsed this path down that I was calling path B earlier. I've collapsed it down into resistance of 12. And then I basically have now collapsed the whole thing down into, here's my 9 ohm. And now I'm saying that the 12 and the 4 pathway that were parallel basically have a resistance of 3. And so now I'm just pretending like my circuit looks like this. And I'm saying that my 9 ohm resistor here is parallel, or excuse me, is in series with this parallel path whose equivalent resistance I've just said is 3. So now I can treat this like it is a series and collapse it down to pretend like my whole thing just has a single 12 ohm resistor. So my voltage is 120 volts. My total resistance in the whole path is 12. Ohm's law, V equals IR. You're going to get a current of 10. 120 equals I times 12. And what is the unit for current?
Amps.
Amps, or A, right? Amperes. All right, so I hope I did not do that too quickly, but it should be hopefully kind of second nature and simple to you guys. I started collapsing this one down into a series whose resistance is 12. I said that all of this is parallel, 4 and 12 is parallel. Use my equation. This whole part of the circuit, therefore, has a resistance of 3. I'm trying to find the current in the 9 ohm resistor. It gets all the current. So I need to figure out the total current. So my equivalent resistance in the whole thing is 12, use Ohm's law. All right. I don't need to use the junction and loop rules. I don't need to use Kirchhoff's rules because I was able to collapse it all down like that. Okay.
Would it have screwed you up if you automatically did go to like a junction rule?
I don't think so. I think it still would have worked okay for you.
Okay.
Yeah. Okay, so part B, I want to know what the current is in the 8 ohm resistor. So this is where I can write one of these equations. I could, maybe almost write loop rules and junction rules just in a simplified form. So I know that right here, I have a current of 10 amps. Maybe I call that I1 or something, coming into this junction. And I know that that current is going to get split in some way down here, which I'll call I2, and down here, which I will call I3. And so really, I'm just trying to figure out, I know that 10 has to equal I2 plus I3. And I know that that current is going to be inversely proportional to resistance, right? So what would you guys do? How could I start to try to figure out? I want to figure out what I3 is, right? That's the current through the 8 ohm resistor. So how could I start doing that?
Figure out the other one instead of
Use,
equal
like-
to the other one.
Sure, there's a way to do it with system of
Isn't it with like I's and R's where you like multiply them together and then they have to like add up to like 0 or something?
Yeah, you do system of equations, right? With the two, because you've got 2 equations. You've got I equals I2 plus I3, and you can draw them for all of the different paths we have here. We can draw I2 R equals whatever it is on the right, because we're gonna have to go over 2 resistors over there.
Okay, so you're saying that I can write a loop rule for this basically, or excuse me, a junction rule right here. And then I can write a
Loop rule.
a loop rule here, and then another one
For the outside loop, you can.
for the big outside loop.
Yeah.
Yeah, I suppose that I could, couldn't I? Sorry, there's just like multiple ways of doing this.
2,
This is on the right path or I3 path?
Can you type it out, please? I don't know who that was or what is
Hey
happening.
Jackson, where are you sitting in respect to your mic?
It was 3.
Jackson is an earthquake. I am Saturn.
Where's the mic?
Round 17. It was supposed to be funny. It's from Wreck-It Ralph.
Why is it so loud?
I don't know.
Okay, guys, let's keep trying to figure this out.
I had a way to do it. Can we hear me, or am I too loud?
No, I can hear you. Yeah, we can hear you now. Yeah, say what you want to say.
Okay. The resistance on I3 path is 3 times the resistance on the I2 path, and you know that it has to split up accordingly, so there would be 3 times as much current on the I2 path.
Yes, so that's correct, and that's what I was trying to think through. So let's make sure we understood what Mr. Wisdom just said. We know that current is inversely proportional to resistance. The total resistance in this path over here, once again, we're ignoring that, is 12, which is 3 times as large as the resistance to the I2 path. So therefore, I can write this statement that I3 has to be, what is that, 1/3 of what I2 is? Is that correct? Because this path has 3 times the resistance. It has a total resistance over here of 12, 8 plus 4, which is 3 times greater. So the current through I2 is going to be 3 times greater what it is in I3. And then I should be able just to, I know that I1 is 10, so I can say that 10 equals I2 plus 1/3 I2, and I can figure out what I2 is and then plug it back in and figure out what I3 is. What's up, Mr. Williamson?
So, let's say I've thought about this, like, and just reasoning through it by, like, creating, like, a proportion and then just flipping them based on resistance, and then just, like, flipping the currents, let's say, whatever the ratio is going to be, like, the inverse of that. Let's say you have 3 parallel branches. Would you just start by, like, collapsing 2 into 1 and then deciding how much current goes to which end based on, like, those inverse, and then just breaking down the one that's made out of 2 and then just further dividing it? Or
Yeah, you can totally do that.
Okay, cool.
Yeah, very good. Yeah, let me remind you guys, another thing that we're kind of using without saying it here is that whenever you have resistors in series, they always get the same current. And then whenever you have branches in parallel, what's the same about them? Do y'all remember?
What?
What's the same about branch? So things that are in series have this. Yeah. Okay. Yeah. So things that are in series have the same current or charge, but things that are in parallel will always have the same voltage. In other words, the voltage drop. You guys remember that term? The voltage drop across this whole path has equal to voltage drop across this path. And that's basically what we're saying that allows us to create this equation right here, because they have to have equivalent voltage drops. That allows us to kind of implicitly use Ohm's law to say that, oh, the current through here then must be, because the resistance is 3 times greater, the current must be 3 times weaker than the current through this path. Anyway, let's try to solve this and actually get a value. We get 10 equals 3/3 I2 plus 1/3 I2 would be 4/3 I2. So it looks like I2 is going to be something.
2.5. Wait.
I2 is 7.5, and then therefore I3 is 2.5. Yes, that's our answer. Have I lost anybody on that? Does that make sense to everybody? You could, if you wanted to, you could use a loop rule. So maybe it would be worth our time to talk about how we could use a loop rule real quick. So let's look at that. There's got to be a way to, what does this do? Just like delete things? Can delete. Ooh, boom. Okay.
You delete the words.
Oh, does it grab that? Whoa. I have so much power right now. Okay. So here I've written a junction rule. The junction rule says that flow in has to equal flow out. And then we could try to write a loop rule. So I can write a loop rule for this maybe, and that might be all that I need. So let me start right here and go down the loop. So loop rules are all about voltage drops and voltage gains, right? So I can say that I have a voltage drop across the 8 ohm resistor, and V equals IR, so negative I3 times 8 would give me the voltage drop there. I get another voltage drop when I cross this resistor, negative I3 times 4, and then I'm coming around right here, and now I'm going opposite what the current is. So that's going to be a voltage gain. Do you guys remember this? Plus I24 has got to equal 0. And so that gives me, I know that I1 is 10. That gives me 2 equations with 2 unknowns, and that's all I need to figure this out. And you should be getting the same answer. This would be what, negative 12 I3 plus 4 I2 equals 0. Yeah, we're gonna get the exact same thing that we had where I2 is 3 times as big as I3. Yeah, neat. Okay, so part C, the potential difference across the 30 microfarad capacitor. Any thoughts about that?
0.
Do what?
0.
Why?
Because it's after a long time.
Because it's full.
We've already stored up the amount of charge that the
0
capacitor can, so now no more charge can flow that way, so there's no more.
So like no more potential difference, right?
before I try to argue it.
Shouldn't it just be the potential difference of the whole circuit? Just 120?
Oh,
Wouldn't it be 0 at the beginning?
it's 0 at the beginning, and
It's going to have a potential difference now. It's just going to be.
No, it's the potential that the 4 ohm receives.
Yeah, it's because it's in parallel to that.
yes. I believe that is correct. Yeah, it's not going to be 0 because we have, the capacitance is 30 microfarads, so 30 times 10 to the negative 6, and that's equal to the ratio of charge over the potential difference that it has. It started with a charge of 0, and the charge slowly built up, which means that the voltage slowly built up because the charge is just going to be equal to, if I rearrange this equation, C delta V. So just as the charge is building up, the potential is also building up. So yeah, I think that we do have to recognize that the 30 microfarad capacitor is in parallel with this 4 ohm resistor. Was that Mr. Jarvis who said that? So I believe that's correct, Mr. Jarvis, that we can just figure out what the voltage drop is across this, and that has got to be the voltage right here as well. Yeah. So we know that the current in this whole path right now is, what was it, 2.5 amps. So it looks like the potential difference, the voltage drop that pathway right here has is, oh, wait a second. No. Yeah, we're doing this correctly. So V equals IR, so 2.5 times 4 is going to be 10 volts. So I think that this is going to have a potential difference of 10 volts. Let me pause and make sure that I'm not lying to you. So give me 1 second. because sometimes it turns out that I lie to you. I guess.
I'm gonna play copyrighted music so your YouTube video gets taken down.
Don't do that. I'm already having issues with my stupid Instagram videos I make.
Are you actually like have they been taking them down?
Yeah,
That's why you upload 2 day 8s.
the dumb Instagram algorithm has been like misidentifying what song it is. Like it thought one of them was like a clip of a TV show, and it took it down.
You think Instagram could build a?
Well, at least they didn't take down the one of the sign, because then I would be very, very sad.
It's such a good song.
It is. Oh my god, it's been in my head all day.
Oh shoot. Sorry, y'all. Why don't you guys go on and while I'm messing around with this, why don't you guys look at the next question, the energy stored and the energy dissipated. So look at parts D and E. And give me 1 second, and then we will. Okay, sorry about that, guys. Yeah, so we are correct about the 10 volts that we just solved for.
No.
All right, so let's keep going. I know that
Henry?
yeah, he's reading in here. I know that we are almost out of time, so someone tell me part D, how can I find the energy stored in that capacitor?
Do one of those equations.
Yeah, so
Energy?
yep, the potential energy stored in a capacitor. This is on your AP equation sheet. There are multiple equations for this. 1/2 C delta V squared is the one that we want. This is the one, by the way, that if you have a hard time remembering it, it's on the AP equation sheet, and it mirrors exactly the potential energy stored in the spring, 1/2 K delta X squared. So all we gotta do is plug and chug. My capacitance is 30 times 10 to the negative 6 microfarads, right? So 1/2 times 30 e negative 6 times my potential difference we just said was 10, and 10 squared is 100. So whatever that ends up being equal to. Looks like I get 1.5 times 10 to the negative 3. What is the unit for that?
Joules?
Yay. Okay, excellent job. Joules. All right. Let's do this last one, part E, and then we'll be done for the day. At some instant, the connection at point P fails. So where's that at? You guys can see my screen, right?
Yep.
Okay. Sorry. Okay. So where's point P? Okay, right here. So that connection fails. And the current in the 9 ohm resistor becomes 0. Calculate the total amount of energy dissipated in the 8 ohm resistor after the connection fails. So first of all, where is the energy coming from if this connection P up here fails? Where's the energy coming from to even power this 8 ohm resistor?
Capacitor?
Yeah, the capacitor is now discharging, right? So this connection fails. So it looks like the capacitor is now basically acting like the battery. It's going to be discharging, and I'm just going to be concerned then with this closed loop. So I still need charge flowing around a closed loop. So here's my closed loop that I'm worried about. Let's see.
Would some charge not be pulled towards the battery at all?
No, because there's so when the capacitor is discharging, it has got to so when a capacitor charges, it basically is pumping charge onto each plate, and then when it discharges, it wants to rearrange that charge from one plate to another. So it's got to travel through a closed pathway still.
Yeah.
So it has no motivation at all to flow, over here where the circuit is open.
Right.
Yeah. So what was the question? How much energy gets dissipated through that 8 ohm resistor? Any thoughts about how we could start solving it?
Power.
Yeah.
Who was saying something? What's it?
Dominic said power.
Okay. So yeah, excellent. And who remembers a relevant equation that can get me power through this?
I squared R?
I thought it was R squared. It's not.
It's one of them is squared. Is it
I squared?
Is it IR squared?
It is R.
IR squared?
Yeah, I think it's R. I'm pretty sure it's R.
No, that doesn't sound right.
Someone look at their equation.
It's IV and V is IR, so P equals I squared R.
Oh, so I squared.
I was right.
Equation.
Yay.
This equation's on the AP equation sheet. P equals I delta V. And yeah, so it looks like all I need to do then is figure out what the current is flowing through the 8 ohm resistor. Who knows how I can figure out what that is? I need to get the current flowing through that 8 ohm resistor. Does anyone have any thoughts about how I can get that?
We can go back to earlier and just find the current running through that entire loop, right?
Okay.
Give me a second. Let me look at it. Sorry, y'all. Give me a second. Okay, so Sorry, let me pull this back up. All right. So now that this path over here is no longer in play, I have basically two parallel paths is one way of looking at it. I have this pathway here, which is consisting of this 4 ohm resistor in series with this 8 ohm resistor. And it is going to be parallel to this 4 ohm resistor. So what I have to do is recognize that once again, out of the total current that is going to flow around, the 8 ohm resistor is only going to get a, so P equals I squared R. The 8 ohm resistor is only going to get a current that is proportional. Sorry, I'm trying to figure out how I could figure out what the total current is.
Can we use system of equations since we know what it was earlier? Or does it have to change?
No, it's going to be different because now my entire setup is different. It's being powered, so to speak, by this capacitor. Okay.
Make a new system of equations?
Yeah, we're going to have to. I'm just trying to figure out, trying to remind myself how exactly we go about doing that. You know what? I'm going to have to look at this one question a little bit more. We only have like 4 minutes left. So how about this? Why don't you guys give part E, this last part of this question, a try. And we'll talk about it first thing on Friday. And then on the classroom, I will also assign the next 2 or 3 problems for you guys to do. And I want those to be turned in to me tomorrow night. I'm not going to grade for correctness, just completion. And then we'll talk about them on Friday. So I apologize, I'm not prepared to talk about part E right here. I need to take some time to figure it out. All right, so you guys try to do it as well. I will assign the next 2 or 3 free response questions, and then we'll meet back, not through Zoom, but through Google Meetings or something like that. I'll get it all figured out on Friday. Hopefully on Friday too, I'll have more information about the dates for the AP exam and the format and stuff like that. So.
Sounds good. Wish we could keep using Zoom and people would just not be bots, but.
I know. I wish that we could. I'm sorry.
All right.
Out of my hands.
So just wait for homework and that's all we have from you? Wait, watch the classroom?
Yes, correct. And remember that those review videos are available on my Haiku website if you guys want those. Totally up to you then.
Sounds good.
All right. Okay. Thank you guys. Let me know if y'all need anything. Feel free to email me. Oh, you do have that dumb assignment that I gave you to do tonight where you're showing me how you're enjoying the sunshine, etc. Right? So
it's worth 100 points.
I just leave everything 100 points in the Google Classroom. It's not really going to be worth 100 points in eSchool. So.
Dang it.
I told you what I did last night, like 12 o'clock.
You're making me go outside.
All right.
100 points for going outside.
Some people. All right, y'all. Thank you guys for your time. Look at Mr. Prabhudasai. You do have to do it twice since you're in 2 of my classes. Oh, no, you're in 3 of my classes, aren't you? Oh, I didn't assign it for the other one.
You have 4.5 hours of Mr. Thurman.
He does. Isn't that so sad for him? That's really bad for him. Even I can't handle that much time with myself. All right, guys. Bye. Thank you. Have a good day. Get part E done and be looking on the classroom for your next assignment.
Bye.